Slides are visible, I hope. Yeah. So today in this second part of the module 5, let us discuss this one we completed up to LVDT, except the strain gauges I left out because of that it's a big thing that we have to discuss. So strain gauge basically this one. So that problem is there. That's why I came up with the note also. So here, so it's basically a passive transducer. You can see here, it's basically a passive transducer. So which uses passive transducer means which will require external power supply, which requires external power source to come alive. So that is a passive transducer that already we have discussed in the last session. So there are two main categories of transducers, which are active and passive transducers. So this is the passive transducer which requires external power source. And what it will do, the variations or changes in the electrical resistance or resistance in the wires is observed as a strain. Okay. So if you are applying the force per unit area, suppose if you are applying the force per unit area, so by that only we are able to change its length and other diameters, other dimensions. But this resistance of the wire is going to depend on all those things, because we know that by the formula of the resistance of wire, we know that it is going to depend on rho L divided by A. It depends on the length, area of cross section and resistivity. But when you apply the force in particular unit area of the wire, for example, that is going to result into deformation or changes in dimensions of the electrical wire. That would result into change in its resistance. So that change in resistance can be accounted or sensed as a strain. That can be sensed as a strain by the strain gauge. That is by the force on wire. That's what it is. So basically what is happening is there is the main operating principle. So when a metal conductor is either stretched or compressed, its resistance changes due to changes in its length and diameter. That's what I am discussing so far. So this is known as piezoresistive effect. Operating principle of the strain gauge is known as piezoresistive effect. So let us coming back to this one. So there are various types of strain gauges are there under wire strain gauges. If you look at this one, unbalanced resistance wire strain gauges and wire strain gauges. Wire strain gauges is another big category that I will take at the end. So unbalanced resistance wire strain gauges, in that again we got many different categories are there. So this is that's why I am taking this one as it separately today, a separate session for this one, because we need to discuss each and every classification of these strain gauges in detail, along with one important derivation. So under wire strain gauges, the first category that is coming is unbalanced resistance wire strain gauge, and under this again subcategories are there like bonded resistance wire strain gauges, and this one is going to be unbonded. Okay, there are coming under this one. So here you can see under the unbonded strain gauge. So the thin wires which are in the particle of a particular gauge, normally having a diameter of 25 micrometer, are attached on the some supporting structure that is known as a body. Inside this, there is another movable body is there. So a pair of such thin wires having diameter of around 25 micrometer are arranged like this as shown in the figure. Two wires are with the movable arm and another two wires are connected with the body also. We can see here applying the force here. There is a linearly we are applying the force, no any angular application of the force. Means such kind of strain gauge wires are able to measure the strain or force what we are applying. Here you can see force which is applied linearly. When you apply this force linearly, this will result into the movement of this movable arm, and because of that movement of the movable arm, the arms attached with the arm and the body will correspondingly stretched or compressed. And this now will be connected as one of the active arm of the bridge circuitry. You can see here. That is known as the active gauge here. And we got another one dummy gauge that we are using it as a reference. This one. So reference means we are using this because whenever we will get unbalanced condition in the bridge, because of this stretching or compression of the strain gauge wires or movement of the arm, or because of the application of the force. So by how much amount we have to balance, that could be done by using this dummy gauge. So that's why it is known as a reference gauge or reference arm. So with the help of this, by how much amount you are going to balance it, that amount will directly reflecting the amount of movement or deformation or compression or stretching of the strain gauge. And these are known as unbonded because they are not bonded with the body. They are not perfectly fixed. They are moving here. They are not because you can see two wires are connected to the movable and another two wires are connected to the body. They are not fixed with one section here. All the four wires are concerned with both body and movable wire. That's why it is known as unbonded. It is not bonded with any of the particular section here, either with the body or the movable wire. So such kind of arrangement or unbonded strain gauge wires are able to detect the displacements up to 50 micrometer. You can 5 micrometer. Another category under this one, what we are getting is a bonded resistance wire strain gauges. Here also you can see its main feature as you can see in the figure here. This is called a bonded because you can see entire the structure of this strain gauge wire is concerned or embedded this one single body structure. There are no two separate structures here, such as we have movable and body here. And here, any kind of such movable or body, we have only one body. In that, this thin wire having the diameter of less than or equal to 20 micrometer in the shape of this folding. So why it will be here? So in order to overcome some of the drawbacks of this unbonded is able to measure up to 25 micrometer diameter, 50 micrometer displacements. But we want to extend with the help of this bonded. So what is happening here is that why it is not able to detect more than 50 micrometer displacements, because it is limited by the sensitivity of these strain gauge wires. They are not able to detect the displacements more than 50 micrometer. Understand? So here, how we are going to cope up with that one? We are trying to increase the area of sensing of these wires by folding them. By that, the surface area will be increased by if you fold it. So whenever you apply the strain or force on this, that force will be sensed on the large cross-sectional area. So here you can see these strain wires are very straight and they have very less surface area to sense the applied force. sensing of applied force, a very small amount of applied force is sensed by this short surface area. So that will be coped up here by increasing the surface area, which is very large, kept very large, so that it is going to feel that almost complete applied force and going to detect beyond 50 kilometer distance. Understanding? Okay. So that this is all what we discussed about unbonded and bonded strain gauge wires. So in this context, we have to have one important derivation here, normally which has been asked. But one thing I want to tell you, whenever you get a question, theoretical question, don't don't try to use equations or derivations there. This I am telling repeatedly. Whether it is an operation or a theoretical discussion, never use derivations. So gauge factor means what? It is the measurement of sensitivity of a material to the strain. So how much our wire is sensitive to strain. So that is given as a change in resistance to the change in length, the ratio of this. That is known as a gauge factor. Okay, this is how we are going to define the strain. That is a change in length to the origin length. If you substitute this strain in this gauge factor definition, okay, if you substitute this one in the gauge factor definition, so now we can replace delta L by rho, that is a strain. Now this gauge factor K expression now will become delta R by R, numerator will be remaining same, but denominator now we redefined it as a strain represented by rho. And let us see another institution what can, that only thing left out is resistance. So resistance of conductor depends on all these factors, we know it basically. That is rho L by E. Rho length is here, length of wire. Area of cross section, that is circle. Area of cross section, that area of circle is pi r square. Replace resistance, radius by the diameter. So finally we will get the R equal to rho by 4 rho by pi d square. Suppose if we substitute this one back here, so let us see what we can get. So you can substitute that one, we are getting this one, that only we are. So these are all the things what we are observing before we are applying any strain or force on the wire. This is what the strain gauge or K factor we got with this R value. R value is not yet substituted here in gauge factor. Now let us suppose what will happen if we apply the force or a strain on the wire. So when the conductor is stressed because of the strain, length got increased, let us say. If the length will increase, then diameter automatically reduce. So that's how you can see diameter got reduced with the minus sign, it will indicate reduction, D minus delta D. Length got increased, that is plus delta. Okay. So this is R, yes it is called, yes it will indicate stress resistance. Simple R it will indicate unstressed resistance before applying the strain. R, and after applying the strain, what is R? That is RS. Now as the delta D got reduced, it's very small, then if you take the square of that, normal thing, if you take the square of any small value, you will get again very small value, and that can be neglected. If you neglect delta D square from this expression, remove them, you will be getting this RS equation reduced to this form. So practice this one with a pen and paper, you will come to know. Or also you can also refer to the study. Then we'll go for rationalizing this equation. We know that very well. What is rationalizing? Like that, multiplying and divided by the same factor will not affect the value of this RS. And if you go on resolving it, so finally we are arriving with RS equal to this big equation. Again, we'll try to neglect the higher powers of delta L Okay, very small change in the length, that is very small. Then we will get the reduced equation for RS like this. So take the common here for delta L by L, make the substitutions for delta L by L as a beam. Then with these things we are finally we are arriving at these new things. So make the substitutions here in these equations and make them in K. In this equation we can substitute. Finally we are arriving at K equal to 1 plus T. So this is a very important relationship between the gauge factor K and mu. Mu is what? Strain. That is a change in length to the original length, delta L by L. So based on this, we will be having a very simple problems will be there. So let us see if it is there. So here you can see resistance strain gauge with the gauge factor of 2. Okay. So very simple problem you will get. Only thing you should know the derivation. Normally such simple problems will be asked in context with the derivation. They may ask you to derive an expression for the gauge factor, no? Then they will also ask some marks with the 2 to 3 marks, such simple problems. So what else he has given? Resistance strain gauge with the GF, gauge factor is given K, that is 2, is centered to the steel member, which is subjected to strain of 10 to the power minus 6. Strain is a unit test quantity. That's why it is given simply strain of 10 to the power minus 6. The original resistance value of the gauge is 130 ohm. Or resistance. Okay. So calculate the change in resistance. Okay, next, we can make use of this formula and resolve it for finding, because he is asking you to find the change in resistance. So delta R is equal to K. This delta L will go on that side, multiplied into R, because it is divided by R, will get that also go on the side. Gauge factor K is given, 2 can substitute, R is given, original resistance 130 ohm. So delta L by L, that is a strain is given 10 to the power minus 6. So we will get the change in resistance as 260 micrometer ohm. That is very small. Okay. So far we discussed bonded and bonded strain gauges. So getting back to the discussion after the discussion with the classification of strain gauges here, again we will get wire strain gauges. In wire strain gauges, again we have three different subtypes are there. So main speciality or features of these wire strain gauges are very fine and thin wires are used here, and that too we can see in the form of a grid or rosette form, this one, or helical form. So these are by their shape, what way they have arranged thin wires, they got their names: grid type, rosette type, and helical type. So idea here is that in a folding type, what they arranged is to increase the surface area, so that to enhance the feeling or sensing sensitivity towards the strain. So accuracy of strain measurement is very much enhanced by increasing the surface area by using such kind of circular structures. So again, we will neglect higher powers of delta L. So another type of this, what we are getting under the wire strain gauges is foil type straining gauges. So it is mainly famous for operating in very high temperatures. It can withstand very high temperatures. Normally in boilers, it has been used to measure the temperatures. So another one, what we are getting, semiconductor type strain gauge, which is famous for using higher gauge factors up to 130 you can use, allows the measurement of very small strains up to 0.01 micrometer. Hysteresis characteristics of such semiconductor strain gauges are
Sir, your
very
voice is
much.
too low, sir.
Hysteresis characteristics of semiconductor strain gauges are excellent in less 0.05%. Life, you can see the life is very much excellent. 10 to the power 7 times you can operate with the frequency response of 10 to the power 12 hertz. Frequency response is very good. Semiconductor strain gauges are also famous for very small in size, come in 0.7 to 7 mm. So these are the main features of semiconductor strain gauges. So in this way, today we have seen how to define the strain gauges, why we are going to study the strain gauges, and how to derive the strain gauge factor with the numericals. And we have seen the classification there. So if you look at the classification once again, unbalanced resistance wire strain gauges, we have came across two types, unbonded and bonded. And under wire type strain gauges, there we came across wire type strain gauges. In that again, the subtype are grid type, rosetic type, torque type, foil strain gauges, and semiconductor type strain gauges. So whenever you get question on this, discuss about strain gauges, you have to discuss all the things except the derivation for gauge factor. So this one thing you remember. So never write derivation whenever you are going to discuss about the classification of strain gauges. Okay. Now let's stop.